Hi, welcome to my channel. My name is Kasia and this is my first such a video. I never thought I would ever show my face on YouTube, yet here we are. Today I want to guide you through creating your TinyML application for person detection, starting from gathering dataset until running inference on the target. I may divide this video into parts, but we will see. Okay, let's start. When I got into TinyML beginning of 2024, I found amazing courses. TinyML from Harvard University on EDX platform and Edge Impulse courses on Coursera. There are some amazing books. TinyML by Warden, he's one of the original creators of the TensorFlow framework, and TinyML Cookbook by Gianmarco Iodice. All of this is a massive knowledge, yet I was missing something. I struggled to create my person detection model from dataset till inference on microcontroller. I did that, I learned a lot, and wanted to share with you. There is a standard workflow for TinyML applications. You first gather the dataset, then pre-process, create model, train the model, convert the model, deploy, and make inference on the target. This part is a standard one for machine learning applications, and this one is specific for TinyML. This could be a whole series on machine learning to cover all of the topics in a thorough way. There is a lot of resources about this already available. I don't want to repeat that or claim I'm an expert. I'll just focus on the specifics for the application. In this video, I am using Arduino Nano 33 BLE Sense with a very basic camera OV7675. But I used also other targets. I bought the TinyML kit with those and a shield to connect them. For best results, it is recommended to take the images with the same camera, as it will be used later. In the description you will find a link to the repositories with all the code. First, the libraries. In your Arduino IDE, go to Manage Libraries and install the following. I created a basic script for a microcontroller to stream the images via serial port. Make sure to select your board here first. If you go to examples provided with the camera library, there is a basic script called camera capture raw bytes. This is a good start and we can build on that. However, I decided to use grayscale to reduce the size, and that's when the weird thing started to happen. The camera libs say that the camera returns 2 bytes per pixel in grayscale. Nothing found in the datasheet though. However, the image I received was either double or I had some kind of a halo effect. To my surprise, the library already filters that, while the method camera bytes per pixel still returns 2. Well, as my university professor told me, never trust any specification. Since we have already cleared this up, let's think about the size of the image. After some trial and errors, I went with 176 by 144, then I scaled to 117 by 96, and then cropped to 96 by 96. Next, we send it via serial port as raw bytes. I made a very basic script in Python to just retrieve the data from serial port. I display the image and prompt whether to save. In a dataset, we need images containing a person and of a background. I checked that 100 of images of each group is a good start. Make sure to take photos with various expressions, best to also add pictures of other people. Let's place the images of a person in a folder with a name 1 and with background in a folder named 0. Let's increase our dataset with augmentation. In a script called dataaugmentation.py, I implemented some transformations of the images. It is a very simple script which creates 8 extra images out of 1. It flips, rotates, and adds noise. All of the 9 images are saved in a new directory, in that case called output. Now we are ready to start working on our model in the file person.detection.py. First we need to load the data, including labels, which are based on the names of the folders. Let's see quickly read image.py. What we need to do here is to ensure we have the proper size of all of the images. Grayscale images are often normalized to -1 to 1 range before training a model in Float32, because that range is centered around 0, which helps neural networks converge faster and learn better. That's what we do here. Back to the main script. I like to always display the image to ensure everything went okay. Next, we convert the labels into one-hot encoding. It creates new columns for each category, where 1 means the category is present and 0 means it's not. We divide the dataset into training and validation portions. Let's create the model. I do it below in the getModel method. I have previously saved this model into a file, and let's see the visualization performed with Netron, as I believe it's easier to have a full picture this way. We are going to use convolution layers with rectified linear unit ReLU activation function after each. The ReLU just makes sure that no output is less than 0, setting any negative results to a minimum of 0. It introduces nonlinearity. The convolution layers have filters that spot patterns, the features. Max pooling and dropout help decrease the number of computations. It performs downsampling. This is a huge simplification. Please refer to other resources on machine learning. Then we have flattened to reduce the dimension of our output from previous layers. We lose spatial information here. We end up with a 1D vector and we feed it to a dense, fully connected layer. The last one is a softmax function that gives us the result of our classification, a value for each of our classes. Their sum equals 1. This is the corresponding part in Python, and let's see it in a different way. First we have a convolution layer with 8 set of filters 2x2. That results in 8 maps. After max pooling we have image of 47 by 47. Next one is a convolution layer with 4 filters 2x2. This one is looking for more complex features. After max pooling we have 22 by 22 image. Next part is the network input, which needs to be a 1D vector. This is why we need to flatten it. Next is a dense layer with a dropout which randomly deactivates neurons. This helps with overfitting. The last one tells us the prediction. We could use a sigmoid, as this is a binary classification, but softmax does the work as well. It gives us the score, how probable the certain class is. We are looking for the highest value. Back to Python. Let's print the summary. And we are ready to train. It's always nice to see how the training goes with the accuracy and loss, so let's prepare that. Next step is to validate the model using the dataset we have previously set aside for the purpose and save it. Let's see the script in action. In this video, we've gone through standard process for model creation. I will cover the TinyML portion in the second part. Thanks for watching. I hope you enjoyed and learned something despite my lack of video editing skills. Like and subscribe maybe. Thanks.